the general principles. Okay, the basic principles of the mass spectrometry. Okay, and then we have seen how the spectra will be represented. Okay, and then the terms we then modes of fragmentations we have seen, general rules for the fragmentation we have seen, and how the bonds will be cleaved we have seen. Okay, so then that is a basic principle part. Okay, so whether it is a sigma cleavage or it is a that is or homolysis or heterolysis or
Electrolytic.
yeah, fragmentation by rearrangement or fragmentation by scrambling or any of the fragmentation by hydrogen transfer or whatever it is, double hydrogen or single hydrogen, whatever it is. So those are the basic principles of fragmentation. Okay, so next coming to the
Sorry.
so next coming to the interpretation part. Okay, so here once if you have a data with you, so how to go through the data, so here and get the information about that particular analytical molecule. Okay, so here we have first class we take, that is saturated hydrocarbons, and saturated hydrocarbons, these are the following, that is following characteristics of the mass spectrum of alkanes. So the here the relative mass of the, okay, parent ion, that is molecular ion peak, okay, will be less. Okay, and as you go on increasing the mass of the homologous series of the alkane, so molecular ion peak will be reduced. Then you will find, normally you will find molecular ion peak, but this molecular ion peak will not be that intense, and as well as you go on increasing the molecular ion, that is mass of the, okay, in a homologous series, then the intensity of the molecular ion peak will be reducing, and then here the peaks generally they will be separated by 14 mass units. So this 14 mass units indicates that, okay, so CH2, suppose if we take that in a propane, you have the CH3, then CH2, then CH3. Okay, so here two CH3s are separated by 14 mass units. So here generally peaks will be separated by 14 mass units. Okay, that represents the CH2 group. So here, and then the largest peak in each cluster, okay, represents, okay, here Cn H2n plus 1 fragment. So this you have to remember for that, and later you can have CnH2n or CnH2n minus 1. So here in mass spectrum of the alkanes, if we see that the largest peak normally it will be of CnH2n plus 1. Okay, that is molecular ion peak, and this is accompanied by, again you have CnH2n or CnH2n minus 1. So, and this fragments corresponds to the loss of 1 and 2 hydrogen atoms. Okay, so CnH2n, so first fragment will be of CnH2n minus 1, that is plus 1, and CnH2n and CnH2n minus 1. So this is basic characteristic of features of uh, that is saturated hydrocarbons or alkanes. So you will have a molecular ion peak, but the molecular ion peak intensity will be less, and as you go on increasing the mass of your straight chain alkane, the intensity of molecular ion peak will be reducing, and you have the peaks are separated by 14 mass units. This 14 mass units corresponds to CH2. Okay, and then the peak will be generally largest peak will be of CnH2n, okay, plus 1, and then you will have other peaks also, that is because of the loss of hydrogens, loss of 1 or 2 hydrogens. Next, branched chain hydrocarbons. So the branched chain hydrocarbons, okay, so they also will have, you will have the molecular ion peak will be appearing, but it is will be very low intensity. And when we were discussing the Stevenson's rule, so we already discussed that there branched chain alkanes, the preferred cleavage at the substituted carbon. That because you will get the stable carbocation or stable fragment ion. So that's what you have to see. Okay, here the main feature you have branched chain alkanes. If you see that the molecular and peak will be appearing, but it will be very less intense, and here bond cleavage takes place. Okay, a fragmentation takes place at the carbon that is substituted, because if cleavage takes place there, you will get the stable carbon that is fragment ion. Okay, and generally large substituent at the branch is eliminated. So this also remember, this point also remember, that largest substituent at the branch is eliminated as radical. Okay, and the radical achieves the stability of delocalization of electrons. And why radical is be removed? Radicals also you have studied the stability of radicals. Okay, how they are stable, and carbocations, carbanions, their stability you have studied. So if you have more number of fragments, okay, that is if you have a branched chain, okay, so you will have the more number of fragments because of the branched chain. So here, if the straight chain alkane fragmentation, so this is you just go through this point, and in straight chain alkanes, fragmentation occurs through loss of methyl group. Okay, so leading to that gives you M minus peak, that is M minus 15 peak, M minus 15 peak. So here you can see that here, this is the molecule you have, that is butane molecular ion. So M by Z value is its molecular mass, that is molecular weight, it is M by Z value. Okay, charge by ratio value, that is 58. And then once if it undergoes fragmentation, so and then you have the peak, that is M by Z value 43. Okay, 58 and 43. So that means what happened, there is a loss of 15 mass units. That loss of 15 mass units is CH3 methyl radical. So this is M minus 15 peak, you call it as a M minus 15. Okay, is this M minus 15 peak, you can call it as a, because there is a loss of mass unit of that is 15. And then in general in straight chain alkanes, if you see that, you will have the, in the spectrum, you will have the M by Z values representing M by Z value 29, M by Z value 43, M by Z value 57, M by Z value. Now you can see that this 29, 43 and 57, and then here if you see that 71, 85 and 99. So you will have this. So these fragments, if you see that, there is all, okay, difference. How much is the difference is there between this and this? Wait 1 second. Okay, so now here if you see that, so between that is between 29 and 43, what is the difference?
14.
Okay, and between 43 and 57?
14.
57 to 79?
67. 14.
And 71 to 85?
14.
And 85 to 99?
85 means 95. 14.
Yeah, so here if you see that, okay, in general, in normally if you see that in mass spectrum of saturated alkanes, straight chain alkanes, if you see that, you will have this cluster of peaks, which are separated by 14 mass units, and sometimes you will have the M minus 15 peaks also. So here this is M minus 15 peak, you can see that here this is M minus 15, 43 is M minus 15, that is because of loss of M, that is
methyl group
as a radical. And then you will have the peaks based on your, okay, straight chain, that is the number of carbons present in your straight chain. You will have these peaks. So you will have M by Z value 29, M by Z value 43, or M by Z value, okay, 57. Okay, and these are there, and as well as you will have the M minus 15 peaks also. Okay, sometimes that is there will be a loss of ethene also. Okay, ethene also, there will be loss of ethene as radical. as radical, and you'll have the methyl cation. Okay, methyl cation you'll have, or methyl or ethyl cation, you can have propyl cation. So, but most probably what will be the fragmentation is that, so you will have loss of methyl radical, okay, and then the loss of CH2 units, loss of CH2 units will be there, okay. So that is with the straight chain alkanes. So here maybe then next, coming to the next slide, here if you see, okay, ions that is 43 and 57 are the most stable in the spectrum, okay, the most stable you will find abundantly, you will find in the straight chain alkanes. So in straight chain alkanes, these are the ions M by Z value representing 3 and 57. So in straight chain alkanes, because they are stable. So we can see here, okay, M by Z value, okay. So CH3 represents, okay, M by Z value 29. So but you will find mostly these ions in the mass spectrum of straight chain alkanes, 43 and 57, okay, because these are all, these two ions, if you see, they are the stable ions. So then they may not undergo the secondary fragmentation, but because they can be stabilized. And then carbon, that is compounds with more than 8 carbon, so will have the similar spectrum, okay. And then you can identify them based on their molecular ion peak. So next one is the branched chain alkanes, we were discussed in the previous slide. So always you have the, so here if you see that, okay, this is 1, 2, 3, 4, 5, 6, 7. So it is, what is the compound? What is this compound? Can you tell me what is this compound? Okay.
1, 2, 3, 4, 5, 6. 1 methyl.
Isoheptane, sir.
4 methyl heptane. Okay. 4 methyl. 4 methyl.
Heptane.
4 methyl heptane. So here if you see that, and we were discussing then the fragmentation rules or Stevenson's rules. So here you see that fragmentation happens at the substituted carbon. So the fourth carbon, it is substituted carbon, right? This carbon is a substituted carbon. And then one more thing also we learned, that largest substance will be eliminated as radical. Okay. So here you have the methyl group. Here you have the substituent on this carbon. Methyl group substituent is there. And then you have the substituents here. That is propyl group also is there. So which is the largest substance? Propyl group is the largest substance. So for that it will be eliminated as radical. So this is about the, okay, branched chain alkanes. So in the branched chain alkanes, what happens is that, so fragmentation happens at substituted carbon, and when elimination takes place, largest, okay, largest substituent that will be eliminated as radical. So that is what here happens with the branched chain alkanes. So this is the simplified example for your mass spectrum of a straight chain alkane. So you can see that, okay. So all the peaks you can see that cluster of peaks you can see M by Z value, okay. M by Z value you have, this is a molecular ion peak at the end of the spectrum. You can calculate if you want, okay, octane, okay. So that will be the molecular ion peak, you have that at the end of the spectrum. Then fragmentation takes place, bond by bond it will be cleaved off, okay. And then you can see that cluster of peaks, okay. This cluster of peaks, if you see that 29 and 48 and 57, 70, 71 and 85. So these are all separated by 14 mass units, because you have the elimination of CH2. Here you have CH2, here you have CH2, 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 CH2. Okay, so sometimes I told you also there will be a possibility of elimination of ethene also from the straight chain alkane. So that possibility also you will have. Okay, so and this is a, and as I told you, so here M by Z value, that is 43, or M by Z value of 57, or okay, will be having high intensity because they do not undergo the secondary fragment. They may not be. So here you have M by Z value 43 is 100%. Okay, and then you have the M by Z value corresponding to that M by Z value 57. So these are the prominent peaks in the straight chain alkanes. Prominent, that is M by Z value. So 43 and 57. Okay. So by these two peaks you can identify, okay, it is a straight chain alkane. So if you have a mass spectrum cluster of peaks which are separated by 14 mass units, then definitely you can say it is, you can see all these peaks are separated by 14 mass units. So then generally you can say that, okay, it is a alkane. Okay, and next point is that you have to determine that same thing may happen with the branched chain alkane also. Branched chain alkane, this is straight chain alkane and branched chain alkane. So you will have the same separated by, the cluster of peaks are separated by 14 mass units, but that you have to determine based on the characteristics of again the peak, again the mass value or intensity of the peaks, you can see. So now here M by Z value 43 is the highest, okay, intense peak, and then next comes you have the M by Z value 57. So that is for straight chain alkanes, and the cluster of peaks you can see that they are separated by 14 mass units, and at the end of the spectrum you can see that the low intensity peak of molecular and peak. So you can calculate the molecular weight of the, okay, here octane, and then you will come to know what is the molecular weight of that. And this is how the fragmentation happens, and fragmentation here you see that it will be of homolytic cleavage, okay, simple cleavage, that is. This is methyl heptane. So methyl pentane, this is a 2,3-methyl pentane. So now the thing is that, so if you have this hexane, okay, hexane, and then if you have a 2-methyl pentane, 3-methyl pentane, so mostly the molecular weight will be same. And here it is a branched chain, branched alkane. So and then you can observe that M by Z value 86 is there. 86 is there. So and then this is a substituted alkane, branched one, and previous one, if you see that this is a straight chain one, you can see the intensity of the molecular ion peak. And then next one, the substituted, that is branched alkane, you can see the M by Z value, that is molecular. And as I told you, at the end of the spectrum generally you will have that molecular ion peak, and this molecular ion peak you can see that it's very, intensity is very low. You may not be, sometimes you may not be able to identify also. So that is because when the substitution increases, so the fragmentation will be of too extensive. It undergoes too extensively fragmentation, and you may not be able to get the molecular ion of branched chain alkane to reach the detector. And then now, how to identify? Okay, here that is whether it is a branched one or straight chain. So now you can see that here M by Z value 57 and 71. Okay, they are very low intense. And whereas M by Z value 43 of straight chain is of 100%. And next, coming to our straight chain, so now M by Z value 57 has become, okay, 57 has become high intense, and whereas M by Z value of 43 has become, okay, is very low intense. So this is the difference between your straight chain alkane and a branched chain alkane. So this way you can identify whether it is a straight chain alkane or a branched chain alkane. So let me come to you. And yeah, did you get this point here? How to identify? Hello.
Sir.
So did you get this point?
No, sir. That how we can identify that branch and unbranch by seeing that signal.
So that's what you can see that here. M by Z value 43 is 100% here in straight chain alkane, right?
Yes.
And 57
Yes,
or 71 if they are very low intense. At the same time, you go to here, okay, M by Z value 759, what a straight chain branched one. This is a branched one, 2-methyl pentane it is. At the third position, methyl group is substituted, okay, and write down the structure. Can you write down the structure?
3-methyl pentane.
Yeah, 3-methyl pentane.
Eight, 4, 1, 2, 3.
Yeah, if you have written down.
Yes, sir.
Yeah, if you have written down the structure, so you can see that this is a molecular weight. Then one of the methyl group is removed. That means 15 is removed. Okay, from that, and because so at the substitution, the fragmentation takes place, and one of the methyl group is removed. Okay, so you have the loss of methyl group. You have this 71. Okay, and then M by Z value 57. So this is a 100% intense. Whereas in straight chain, if you see that this is 43, Z value 43 will be the 100% peak. And in straight chain, branched chain alkanes, these two values, 15, 57 and 71 will be highly intensive, and this will become low intense. You can see that here it has become low intense, and this has become high intense. So by seeing this too, you can say that, okay, whether it is a straight chain alkane or a branched alkane. So in straight chain alkane, this will be intense, and whereas branched alkane, this will be intense. M by Z value 57 or M by Z value 71. 71. These two will be of intense peaks. Next, okay, so you can, that is as I told you that you can add. Next one is that cycloalkanes. How you differentiate that we have seen in the examples. That is, okay, so whether it is a straight chain alkane or a branched alkane, you can differentiate. So with straight chain alkanes, M by Z value 43 will be of intense one, and whereas in branched one alkanes, you have the M by Z value of 51 and M by Z value of 71. That is M by Z value of 57 and 71. These two peaks will be of intense based on the molecular weight. Okay, based on the molecular weight. So you can see that how you differentiate. Next, coming to the cycloalkanes. Okay, so the cycloalkanes, they undergo the complex splitting pattern. Okay, and that is not a splitting pattern, fragmentation pattern, and generally CC bond will be cleaved, and the base peak generally you will have the M by Z value 56. Okay, so here you can see that the bond CC bond will be cleaved. You have the M by Z value. So this is a molecular ion, and then once the molecular ion is formed and will be cleaved, again you have the molecular ion, that is M by Z value 84, and then you have the fragmentation. Okay, then you have the fragmentation here. Okay, so one way here CH3 radical will be removed. CH3 radical will be removed. You will have the M by Z value of 69. This is ion and fragment ion. And another way you can see that you will have the removal of ethene. Sometimes ethene also, I told you, in the straight chain alkanes or branched alkanes, this also will be removed as a neutral molecule. Neutral molecule, and M by Z value 56 will be the prominent peak. So this is, you have to understand. So this is the base peak. M by Z value will be of 56. For cyclohexane, you see that first molecular ion is formed by knocking out of one electron. That is the molecular weight of the cyclohexane is M by Z value, that is 84, and then you will have the the CC bond cleavage, and then this is M by Z value. Again, it is a molecular, nothing is lost, fragmentation has not taken place, only CC bond cleavage happened. Now the fragmentation happens. So this undergoes the fragmentation to give you different fragments. So the one of the fragment will be of, anyway, it will be of radical, another one will be of fragment ion. And second, there is a second way also fragmentation. So here also M by Z value of 56, and by loss of ethene molecule as a neutral molecule. So this will be the prominent peak in the cyclohexane. So coming to the example, so cyclohexane, you can see that. Okay, so this is a cyclohexane. So there is a complex splitting pattern. You have the M by Z value 69. So this represents M by Z value 84. What it is? So you can see here in cyclohexane, the molecular end peak is very intense compared to the your straight chain alkanes and branched alkanes. And cyclohexane, because it is cyclic structure, it can be stable. It can be, this is cyclic structure, molecular ion will be stable. That's why the molecular ion peak intense will be, you can see that there is a high intense peak. Next, 100% abundantly available ion is that you have the MZ value 56, that is because of loss of ethane. And then again MZ value, you can see that, you can see that here 69, that is because of loss of methyl radical. So these are further fragments, MZ value 41 and MZ value 27, that is further fragmentation happens. But the prominent peak you can identify, it is MZ value 56 in cycloalkanes, and that's what how you can differentiate. Next, alkenes. So alkenes, so you will coming to the alkenes. So here you will have the molecular and peak will be of so intense peak you can find, because you have the double bonds in them, alkenes, and they can be resonance stabilized. And an alkenes, generally what happens is that they generally try to undergo the allylic cleavage, and sometimes you will have the McLafferty rearrangement also. So here two things, 3 or 4 things, features you can find. So the molecular ion peak, the features, if you see, the molecular ion peak generally it will be intense peak. That is because of the presence of double bonds. Molecular ion, prominently you can find out the molecular ion peak. And next one is that you have the next one is that you have the cleavage. So the cleavage, if you see that, so generally it will be of allylic cleavage you can find, because allylic cation is more stable, since it can be resonance stabilized. And then other one you can see that it can undergo the McLafferty rearrangement. McLafferty rearrangement, I told you, McLafferty rearrangement. So if you have a gamma hydrogen, so this gamma hydrogen will be transferred. Transfer of gamma hydrogen will be there, and you will have the McLafferty. One is the stable cation and another one is olefin. You will stable olefin as a neutral molecule will be removed in the McLafferty rearrangement. So here in one, that is one pentane, for example, I have given you the one pentane, you have the gamma hydrogen. The gamma hydrogen will be transferred here, and then you will have the removal of allylic cation is there, and as well as McLafferty rearrangement is there, and there is a neutral molecule, that is olefin. Ethene is removed. So the ethene will be removed here. And cyclic olefins also show up the peaks of which are 14 mass units apart, generally. So they are, because in cyclic they have the CH2 units in cyclic olefins. So general mode of fragmentation, allylic cleavage, and then fragments may be formed by the McLafferty rearrangement. So, and here you can see the McLafferty rearrangement because it is a gamma hydrogen, and then you can see here allylic cleavage. Allylic cleavage means double bond, single bond. So allylic cation is formed, and an MZ value of 42. MZ value of 42 is very prominent peak. MZ value 42 is very prominent peak in alkenes, where you have the double bonds. So the characteristic features are this. MZ value 42 is the prominent one, and you will also find molecular ion peak intense because you will have the double bonds. And then allylic cleavage is the preferred one, and sometimes McLafferty rearrangement also happens. So this is a for example, I have given you here, that is one pentane. So one pentane, if you see that here, molecular ion peak, that is the molecular ion peak, the molecular weight you can see at end of the spectrum. End of the spectrum, you have that MZ value, that is 70, that is a molecular ion peak. And then you have the here, here you can see that there is a loss of MZ value 42. MZ value 42, I told you MZ value 42 will be, here you can see MZ value, that is a 42 loss of, here CH2, that is 28. M minus 28 peak you can find out in this here. Okay, -1, 28. Or you can also have the here allylic cleavage. Allylic cleavage, that is also there. So this is a McLafferty rearrangement peak, that is a 42. And are you getting here my point? Wait 1 second. Okay, you are getting my point here. One pentene structure, you know. So one pentene, hello?
Yes, sir.
Yeah, are you getting my point here? So thing is that this is a one pentene mass spectrum. Here how it looks like. So at the end of the spectrum, if you see that molecular ion is that it is MZ value 70, that is molecular ion peak, because it is intense because of presence of double bonds. This is M by Z value, that is 55, that is the loss of CH3 is there, 15 M minus 15. And then here you have M by Z value 42 and M by Z value 41. Okay, so this 41 represents the allylic cation and M by Z value 42 represents the McLafferty rearrangement. McLafferty rearrangement I have shown you here in the previous slide. If you see that gamma hydrogen is transferred. Okay, so M by Z value 43 is there, right? One is the M by Z value 43. Without that is hydrogen will not be transferred here. What happens? Directly CH2 will, that CH2 CH3 will be cleaved off, because that is allylic cleavage. Allyl group, you know, right? This is the allyl group. Allylic cleavage happens here. Directly CH3 will be removed off. Whereas in McLafferty rearrangement, what happens? Before cleavage of this, hydrogen will be transferred here. Okay, and
To oxygen.
yeah, so M by Z value 42 will be there. And if hydrogen is not transferred here and cleavage happens, then this fragment will be of M by Z value 41. So M by Z value 41, M by Z value 42 when this hydrogen transfers here. Okay, so those two peaks prominently you can see that this is because of M by Z value 41 is because of the loss of CH3 CH2, and whereas M by Z value 42 is because of loss of CH2 double bond CH2, and this is allylic cleavage and this is McLafferty rearrangement. Because of the McLafferty rearrangement. You know the McLafferty rearrangement, that is there will be a gamma hydrogen transfer. You got this?
Yes, sir.
Okay, these two peaks prominently you can find in the alkenes. Okay, so alkenes characteristics are, sir, if you see that one is you will have the prominent molecular ion peak, and then there are other peaks also which are very prominent. This is not only the characteristic feature. Okay, with this you cannot say what it is, but molecular ion peak will be intense, because this intense peaks we cannot find it in the saturated alkanes, whether it is a branched one or straight chain one. Only you can find that intense peak in cycloalkanes. Okay, and here the prominent peaks, characteristic peaks, you have to see that. Okay, M by Z value 41. So this is highly prominent peak you can find, and this is because of allylic cation. Allylic cation you can allylic cation you can observe only in the alkene case, because they have the double bond in it, double bond with them. And then next one is that is so it is only for the one pentane. Okay, this M by Z value 42 is one pentane because of the